This video demonstration will showcase the current progress of Task 5.4 of the Resilmesh project, Attack Mitigation. We will be evaluating the new and improved architecture of the Mitigation Manager component, and discuss the implications of integrating an AI planning engine within the mitigation process. First, let's get an overview of the relevant components. The Attack Mitigation task focuses around the security operations layer, highlighted here in red. This part of Resilmesh is in charge of deciding the most suitable responses against security incidents, by identifying attacks and adversaries and orchestrating mitigation actions against them. The Mitigation Manager component is tasked with the decision-making process, and is aided by the Playbooks tool and Workflow Orchestrator components to enforce mitigations in the form of COA playbooks. We will be focusing on the Mitigation Manager component, as it is the component with the most changes when compared against the previous iteration. The Mitigation Manager initiates the attack mitigation flow when receiving a security alert from Wazoo, through a NATS message queue. The component makes use of the cyber situational awareness and risk score information available through the ISIM component to enrich its internal state, used to run the AI planning phase in order to obtain a mitigation plan. Finally, the Mitigation Manager will trigger the execution of the obtained workflows through the Playbooks tool and Workflow Orchestrator components, as well as initiate any pen testing exercise through the AI-based automated security testing component. Featured in the updated attack mitigation process is the integration of an AI planning engine for the decision-making process. To achieve this, we have rewritten the Mitigation Manager component in Clojure to take advantage of the OptiPlanner AI constraint solver. OptiPlanner allows us to model our attack mitigation problem as a set of entities, variables, and constraints, which can then be iterated upon by the solver in a highly efficient and optimized process in order to obtain the solution state that best suits the situational requirements. The attack tracking logic from the previous implementation has been ported over and used to enrich the information available to the planning engine, in order to allow it to reach solutions that take into account potential future attacks and the effectiveness of past mitigations. Let's demonstrate the Mitigation Manager in a simulated scenario. We will be running the component on the full-screen terminal. On the second terminal, we will trigger a REST endpoint to manually publish Wazoo alerts. We will simulate two mitigation flows using two alerts. The first scenario is triggered by a remote connection using NCAT, and is mitigated using a playbook that terminates the connection. The second scenario is triggered by the change in permissions of a local file, mitigated by enforcing the deletion of the file. Let's publish the first alert. Immediately after publishing, we can see the Mitigation Manager updating the local state, running the AI planning engine, obtaining a solution, and executing the selected playbook. Note that for demonstration purposes, we have configured the Mitigation Manager to spend 1 second in the solver phase. In the logs, we can spot that the attack state has been updated after receiving the alert, since it has triggered an attack node corresponding to an NCAT remote connection. Let's publish the second alert, and see how the Mitigation Manager responds. The mitigation process is the same, but we can spot a few differences in the output. First, note that the state has been updated once again, since the alert has triggered the next node in the attack graph. This is also reflected in the final mitigation solution, which this time references the file deletion workflow. Modeling the attack mitigation scenario as a planning problem allows us to easily encode new business logic in the form of OptiPlanner constraints. Hard constraints are used for critical requirements, such as the mitigation of all alerts above a certain risk threshold, while soft constraints are used to prune the valid solution space in search of the optimal one, like incentivizing mitigations with low associated costs. We have modeled the planning problem so that an upper limit of mitigations per solution can be specified, as well as to allow the solver to return no mitigations, if a suitable one cannot be found with the provided constraints. Our model also accepts more than one alert per run, which allows us to batch multiple alerts together to further enrich the data fed to the solver. When evaluating solutions, constraints can be adjusted at runtime and solutions can be calculated in parallel, allowing the Mitigation Manager to quickly and efficiently obtain a wide array of mitigations suitable for the specific scenario. Finally, a time budget for the AI solving phase can also be configured, a critical feature for mitigation of time-sensitive attacks.